looking at the energy cascade, we want to focus on eddies. An eddy, as we have seen in the flow visualization clip, can be difficult to define, but it basically is any motion that contains energy. Turbulence also plays a role in the energy cascade and is defined here as eddies of different sizes and can be quantified by the Reynolds number. The Reynolds number is a dimensionless number that can be used to predict flow patterns or when a flow will become turbulent. So here we see the Reynolds number equation, and here we have rho as the density times u, which is the velocity with respect to the object, times L, which is the characteristic linear dimension, all over mu, which is the dynamic viscosity. This also can be written, as you can see, as just U times L over V, where V is the kinematic viscosity. So the main takeaway here is that when we have high Reynolds numbers, we have lots of turbulence and large eddies. When we have low Reynolds numbers, we'll have low turbulence and small eddies. With these two concepts together, we can define the energy cascade. And that is, as the largest eddies, being the large-scale motion, transfers energy to the smaller eddies, the small-scale motion, which then can break up into even smaller eddies, and so on and so forth. Now, to illustrate this, imagine a large fan spinning, creating a large vortex. And from that, we'll get smaller eddies that break off, creating their own vortexes. And from that, we'll get even smaller and smaller eddies. Now, if we were to zoom in on one of these and blow it up, we would get something that actually looks like our original fan, our original vortex. So this hints to an idea called self-similarity, which in mathematics means that the whole is exactly or approximately equal to a part of itself. And this is what we saw in the large vortices looking like the smaller vortices. A really good example of this idea of self-similarity is the Koch snowflake. Now here, when we look at the Koch snowflake, we see as we're zooming in on this shape, it retains its form on and into forever. So this leads to the big question and the great wonder of the energy cascade. Where does this transfer of big to small eddies end? So the answer really lies to the Reynolds number. High Reynolds numbers means large eddies, and low Reynolds numbers means small eddies. And now, because the Reynolds number is dependent on viscosity, when the Reynolds number is very large, the viscosity isn't important. But when the Reynolds number is low, the viscosity is important. At the very small scales, at the very smallest of eddies, the energy will dissipate into heat due to viscous forces.